A developer just ran a 400 billion parameter large language model directly on an iPhone 17 Pro, with airplane mode turned on. The compressed model requires 200 gigabytes of space, but the phone has exactly 12 gigabytes of LPDDR5X high-speed working memory. Attempting to load a file 17 times larger than available memory has a mathematically guaranteed outcome. The system runs out of memory and crashes. Yet the model successfully generates text. It executes at a rate of 0.6 tokens per second, which translates to about 1 word every 2 seconds. There is no hidden network connection bridging the gap. Every calculation happens directly on the phone's internal A19 Pro silicon. Accomplishing this requires solving 2 distinct physical limits simultaneously: the speed at which data moves from storage to the processor, and the limited space available to hold the context of an ongoing conversation. The first solution is Flash-MoE. This software technique bypasses the physical memory limit by leaving the model's weights permanently on the phone's flash storage and streaming only the active pieces directly to the GPU on demand. The second solution is TurboQuant. This compresses the key value cache, the working memory the model uses to remember the context of your prompt, so the conversation history doesn't overflow the physical RAM. By reverse engineering how this device runs a massive model slowly, we expose the exact engineering mechanics required to bypass hardware limits and run highly capable models at full speed. To see how streaming is even possible, we have to look at the software layer. This model does not function like a traditional dense neural network, where every parameter activates for every single word. The specific architecture here is Qwen 3.5.397B A17B. It is built on a mixture of experts topology. A mixture of experts, or MoE, is a neural network design that divides its parameters into specialized subnetworks, activating only a few of them for any given input. This diagram shows a single layer of that model. Instead of a uniform block of parameters, the layer is divided into 512 discrete expert clusters, sitting inactive in a massive grid. When a single token, which is a numerical representation of a word or partial word, passes through this layer, a routing mechanism determines which specialists are needed. It activates exactly 11 nodes, 10 routed experts and 1 shared expert, and leaves the other 501 bypassed. By targeting only the necessary nodes, the active compute requirement for each token drops from 397 billion parameters down to 17 billion. That means only 4.3% of the total neural pathways fire per pass. The structural advantage here is absolute. The system never actually needs to load the entire 400 billion parameter model into working memory simultaneously. However, a 17 billion parameter active footprint still requires more space than the iPhone's 12 gigabyte physical limit allows. Architectural sparsity reduces the math from impossible to merely difficult. But without a hardware-level method to bypass the physical memory constraint entirely, the model still cannot run. Moving from the software architecture to the physical data pipeline reveals exactly how the device bypasses that limit. This pipeline diagram shows the device's internal bandwidth gap. The NVMe solid-state drive can read data at roughly 5 gigabytes per second. NVMe is a high-speed storage protocol used for permanent data retention, but the phone's working memory expects an intake speed of 51 gigabytes per second. To make the execution fit, the inactive expert weights are stored permanently on the flash drive. When the router requests them, the 17 billion active weights are piped directly into RAM through that narrow 5 gigabyte per second connection. That 10-fold gap in bandwidth explains the 0.6 tokens per second execution speed. The physical read rate of the solid-state drive establishes an absolute ceiling for inference. Worse, flash storage struggles with random reads. If the requested expert weights are scattered arbitrarily across the drive, search delays further choke that limited bandwidth. To maximize throughput, the system employs an optimization technique detailed by Apple researchers called windowing. Linguistic generation is repetitive. Consecutive words frequently activate the exact same neural pathways. Windowing caches recently activated experts directly in the RAM, eliminating redundant trips to the hard drive. The second optimization utilized here is row-column bundling. Flash controllers operate fastest when reading sequential data. Row-column bundling takes scattered expert weights and groups them into large contiguous chunks on the drive itself. perfectly aligning with the drive's mechanical preference. By organizing the drive to match how the neural network thinks, the streaming process maps the model's structural sparsity onto the physical storage layout. It converts a fatal lack of memory into a manageable reduction in speed. Returning to the diagram of our 12 GB physical RAM limit, the streaming active weights now occupy a large, stable block of that space. But loading the weights is only half the execution process. The system also has to maintain the conversation history using the key value cache. Every word the model generates drops a new permanent piece of state data directly into the RAM, allowing the model to remember what you just asked it. As the conversation scales, this cache grows relentlessly. Eventually, it presses against the space required for the active MoE weights, creating a conflict over the remaining physical memory. To prevent this memory starvation, developers apply an algorithm published by Google called TurboQuant. TurboQuant applies aggressive numerical compression directly to the context entries. It does this retroactively, meaning the model requires no additional fine-tuning to accept the compression. The algorithm achieves a 6x memory reduction without degrading the structural accuracy of the model's outputs. In practical terms, a long conversation that would normally demand 6 GB of RAM is crushed down to fit neatly into a 1 GB allocation. Solving the context bottleneck is as critical as streaming the weights. Neither optimization functions if the other consumes the shared physical RAM. Zooming out from these granular hardware constraints, this specific engineering achievement provides a template for the next stage of mobile intelligence. Running a massive model at 0.6 tokens per second has no utility for an end user, but as an engineering benchmark, it successfully proves the absolute physical viability of storage streaming architectures on mobile silicon. This comparative dashboard shows the exact same 397 billion parameter model running on an M4 Max MacBook Pro, equipped with 128 GB of unified memory. On that machine, the inference speed spikes to 19.98 tokens per second. That 33x increase in speed demonstrates that the MoE streaming technique scales linearly. Give the architecture a wider memory bandwidth pipe, and the latency vanishes. Applying these techniques to future hardware yields a strict division of labor, the Butler versus the consultant. The Butler is an optimized 14 to 30 billion parameter MoE model. Using flash storage streaming and context compression, it runs entirely on device at fluid conversational speeds. This schematic shows a secure, closed-loop system. The Butler model manages personal inputs, health, location, and private messages, entirely enclosed by the phone's firewall. For heavy reasoning, the system tags in the consultant, routing only abstract prompts to massive cloud models. This split guarantees personal privacy through the absolute physics of an air gap, rather than relying on the terms of service policies of a cloud provider. The physical limitations of mobile silicon are fixed, but by mapping software sparsity directly onto those physical constraints, engineering has removed hardware capacity as the absolute barrier to local intelligence.